Okay, so this video is my 7th video in this vector calculus series, and finally we're going to get into some actual vector calculus. And in this video I'm going to introduce you to the concept of line integrals of vector fields. Okay, so I know I haven't discussed vector fields yet, so I'm going to do that in this video, and then I'm going to introduce the concept of line integral. So there's a couple different kinds of line integrals. This particular type of line integral that I'm going to be calculating is described as a line integral of a vector field. And in physics, one can think of it as the work done by a vector field on some moving particle that's moving on like a fixed path or a line or a curve. Okay, so I'm going to show you what I mean. I have this little MATLAB script here, and what I'm going to do, I'll discuss these equations in a minute, but I'm going to show you, when I run this, you're going to see like a XY Cartesian coordinate system with a bunch of arrows on it, and that's the vector field. Okay, so you can think of each vector as if like a force field or something like that. So I'll show you what I mean in a minute here, but after a second or two you're going to see a little red dot move across the vector field, and that's going to be the particle moving across the vector field, and the path that it takes, or the trajectory, that's like a fixed line or a fixed curve that the particle takes, and we're going to compute the work done by the vector field on that particle as it moves along that line. Okay, so here's a vector field. You can see up here there's a particle. You can see the particle moves through the vector field. Okay, so the way you interpret this is like maybe this coordinate system is like a plane. Okay, and if you were to insert a particle, let's just say at this point right here, then there would be a force with a magnitude and a direction that would push that particle like in this direction, right? So that's not the interpretation that we're using for this example, but you can think of the vector field as if, like, let's say you're to put a particle right here at rest, then there would be a force acting on it in this direction, so the particle would begin to move in that direction, and then you could see that it would follow these force vectors, and since they're getting smaller up here, maybe since force is related to acceleration, maybe it has some velocity but it's not accelerating anymore, and then right here there's no force acting on it, so it would be sort of like moving freely here, and then as it went up this way you would see that there's forces acting down on it, so it would begin to like decelerate since force is proportional to acceleration, and then maybe the particle would like stop somewhere up here and then begin to accelerate back down. Who knows? But what we're talking about here is maybe there's like some fixed rail or something like that, some fixed path, some fixed line, and there's a particle that's on that rail, and the particle is being moved along that rail in this vector field. So the vector field, you can see here, is pushing back on the particle, like trying to slow it down, right? So you know hopefully from physics, that if you were to push a ball, or you were to push a crate or something like that, and you were successful in displacing the crate, then you are doing work on the crate, and you are doing positive work on the crate. That's how we define it. Well, what about if the crate was coming towards you and you were pushing on the crate and you were trying to slow it down, and you were unsuccessful at slowing it down? Or let's say you slowed it down, but the point is, relative to you there would be like this negative displacement until the crate slows down and stops, and so in this case you would have done negative work on the crate. So in this case here, the particle is moving through the vector field, or the force field, and the force field is pushing back against the particle, and relative to the direction of the force being applied, the particle is moving in the opposite direction, right? So in this case, as the particle moves from here to here, you can see that the force field is actually doing negative work on the particle because it was not able to displace it in the same direction as the force. Okay, so here are some of the equations. So the blue arrows that you've seen, those are described by this vector. Now, if I were to do a vector like this, it would just be some vector that looks like this, right? But with a vector field, the magnitude and the direction of the vector, or the vector itself, depends on where you are, and in this case on the xy plane, which means that its components are functions of x and y. Okay, so you can see here that the y component of this vector field has a square root of x, so maybe the domain of x, maybe x has to be greater than or equal to 0 in this case, because we don't want to take the square root of a negative number. And we can say that maybe y is defined like on all the real numbers, something like that. Okay, so what would this look like? So if we pick the point 0, 0, okay, so let's say we wanted to plot some vectors here. Let's say we want to plot a vector in this vector field at the point 0, 0. So then we would plug in x is 0 and y is 0 for each of the components here, and you can see that the vector at the point 0, 0 would just be like the 0 vector. Okay, so that would be 0, 0. So there's a 0 vector there. What about at the point 1, 1? Okay, so at the point 1, 1, x is 1, y is 1. So the x component would be 1, and then the y component would be, well, negative 1. So right here, the x component would be 1 in that direction, and the y component would be negative 1 in that direction. Okay, so I don't have enough space here to draw it to scale, but let's just say that it looks something like this. Okay, and its length would be root 2. It would go 1 in the x direction and negative 1 in the y direction. Okay, so that would be at the point 1, 1. And this is some scaled version of f at that point, because I don't have enough room here to extend it all the way down here. Okay, so let's pick another point. Let's pick a point like halfway. Okay, so let's just say that this point is halfway. So what would that be? So f of 1/2, 1/2 would be, well, 1/2, this would be 1 over 2 squared, so 1 over 4, and then 1 over 8. So 4 times 8 is 32. So it would go that much in the x direction, and then it would go negative 1 over 2 root 2 in the y direction. So I don't really know what that looks like. I would think that the x component would be a lot smaller than the y component. So I don't know, maybe it looks something like this. Okay, so this is the equation for our vector field. It's just a quick introduction to vector fields. Now I want to discuss the path that the particle takes in the animation that I showed you. So this is why I spent a few videos talking about parametric equations of lines and surfaces, because now we're actually going to use them. So we have a vector field, and when you're computing line integrals of vector fields, the line or the path that the particle moves across would be given to you, or you would have to find as a parametric equation. So in this example, I have that the parametric equation of the line that the particle moves across would be this. Okay, so let's just plot the trajectory of this line here. Okay, so let's plot this trajectory. I made my own axis here because I know that you can see here that as t increases, the y component of this position vector is going to go negative, and the other axis that I had was just the first quadrant, and I actually need the fourth quadrant here. Okay, so I'm just going to plot a couple points. So at t equals 0, you can see that the position vector just points at the origin here, so that's at t equals 0. Let's do the endpoints here. Or in this example, I'm going to do the line integral as t goes from 0 to 1. So the endpoints would be 0 when t equals 0 and when t equals 1. So let's plot when t equals 1. And you can see when t equals 1, you just have the point 1, negative 1. So somewhere here. Okay, and if you were to pick values of t in between here, you would see that, like you've seen in the animation. The particle would start here and then move in this direction down to this final point here. Okay, and we've seen, I'm not going to draw the vector field exactly, but we've seen that it sort of looks something like this, where it was sort of smaller as we were as x and y got smaller here, right? Because when x and y are less than 1 here, you can see that this x component gets really small. So they were sort of pushing back like this. Okay, so I'm going to zoom in on a little piece of this curve right here. I'm going to zoom in to a small little differential segment of the curve right here. Let's just say that the curve is doing something like this. Oops. Right at that point, right? It doesn't really matter what the line looks like. Okay, so if we want to know how much the particle was displaced from the point P to some other point P1, then maybe that's a little vector, a little tiny differential vector that I'm going to write like this. Okay, so it's sort of like, you can think of dr as being like a differential change in the position from P to P1. Okay, now let's say that the distance between P and P1 is infinitesimally small. Okay, so let's just say that at the point P there's some value, we evaluate our vector field at the point P. Okay, well hopefully you remember from high school physics that the work in this case done by the vector field on this particle as the particle displaces from point P to some other point P1, which is infinitesimally small distance away, would be the dot product between the force and that displacement, right? That's what work is. So now, basically, if we were to add up all of the actually, I guess this would be like a differential. If we were to add up all of these little differential work elements all along the length of this curve, right, which would be like this, the integral of this dot product along this curve, then what do we get? Well, when we integrate this differential here, we just get the work, and so this is our definition of work. Okay, well, this C here denotes that, it's along this curve, C, the curve that this position vector traces out. Okay, so I know this isn't a really mathematically rigorous proof or anything like that, but it gives you, hopefully it gives you some intuition about what a line integral is, right? This is a line integral. And one application is physics, where you're computing the work that a vector field does on some moving particle. So the hard part here is figuring out what's dr? What's this notation? What does this even mean? Well, we know that from one of my previous videos that if you differentiate this position vector with respect to time, then what do you get? Well, I think before I was writing a t like this, you get some tangent, some vector that's tangent to the surface, or some vector that's tangent to the curve at some particular point. But in this case, I'm not going to write it as t. I'm going to write it just as r prime. just to simplify things. Right, so the derivative of r with respect to t is just r prime. That's you know, pretty obvious here. So then you can just rewrite dr as r prime dt. Okay, so and this is what you plug into here. This line integral is usually written in terms of this vector, this differential vector here, dr. Okay, but when you actually go to compute this thing, you actually differentiate r, and then you integrate with respect to t, because you have r prime dt right here, right? So let me just show you the example very quick. Okay, so this is pretty much everything I've done so far. So I'm just going to go through this example really quickly, and then I'll do another example in another video. Okay, so we want to compute this line integral. So remember, you can tell by the integrand here, this f dot dr, that dr is some displacement and you're dotting it with some force. So this is some, like from the physics definition, this is work here, right? And then when you see the integral, you know that you're adding up a bunch of little differential work elements, and then this symbol here shows you that it's along some curve, right? So hopefully when you see these symbols here, this notation, you can intuitively understand what's being represented here. So if I wanted to plug in my values for this stuff here, I would have f is this guy right here. So f is just the x component is x squared. So now dr, well, r is this guy. So now if I want to calculate r prime dt, then I just take the derivative of r here. So 2t and then negative 3t squared. Okay, so I plug r prime dt right here. Now you can see that I want to integrate this thing with respect to t. And here I have a bunch of x's and y's. So what do? Well, we know from r that x is t squared and y is negative t cubed. Right? The x component of r is t squared, so that means that x is t squared. And the y component of r is negative t cubed, so that means that y must be negative t cubed. So if we know what x and y is, remember they're parameterizations, then we can plug them in for f, our vector field. So what do we have in this case? Well, we would have x of t squared, so that would be t to the 4. T to the 4 times negative t to the 9, right? Now there's nothing to it. All we have to do is compute this dot product. Alright, I said that we wanted to evaluate this guy as t went from 0 to 1. So I'll do that here. So we have negative t to the 13 times 2t. So that's 2t to the 14 with a negative sign. Okay, and then we integrate with respect to time here. And we evaluate that at 1 and 0. And you can see when you do that we end up with negative work being done, like we thought. That makes sense, that's what we expected. So yeah, in the next video I'll do some more examples, and hopefully I'll be able to describe all this stuff a little bit better. Thank you very much.